Hey everybody, Mr. Antonucci here, and in this video we're going to start covering inverse functions. And at first we're going to talk about how to verify that one function is the inverse function of another function. So first thing we want to get down is that by swapping x and y in each ordered pair of a function, you can form the inverse function of f. Now, the notation for inverse functions is f to the -1, but you wouldn't say that. You would read it f inverse of x. The effect is that an inverse function has on f is that it undoes what the original function did. In other words, if we compose a function and its inverse, so plug one inside the other and simplify, it will always simplify down to x if they truly are inverse functions. The inverse notation, f to the -1, again, you don't say f to the -1 because oftentimes when we think of it as a negative exponent, we think of it as the reciprocal, but that is not the case. So remember, if you had like x to the -2, that would mean 1 over x squared. Okay. But with function notation, if you have the -1 as the exponent, that implies inverse notation, which is not the reciprocal. Here's some important observations that we need to keep in mind. If g is the inverse of f, then f is the inverse of g. Also, since to create the inverse, you swap x and y, the domain of the inverse is equal to the range of f, and the range of the inverse is equal to the domain of f. In other words, the domain and range flip-flop. Also, a function does not have to have an inverse function, but when it does, it is unique, meaning that there is only one inverse function for a particular function. So we're going to show that these two functions are inverses of one another. So the first thing we're going to do is plug one function inside the other by composing them. So in other words, f of g of x, and this is going to say that we're going to put g in for x anywhere there's an x in the first equation. So 2 times g of x cubed minus 1. So I'm going to actually substitute the function in. So 2 times the cube root of x plus 1 over 2 cubed minus 1. When you cube a cube root, they cancel one another. So this would be 2 times x plus 1 over 2 minus 1. The 2's would cancel one another, and then you'd be left with x plus 1 minus 1, which is equal to x. Similarly, we could do it the other way and do g of f of x, and you should get the same thing. So this would be the cube root of x plus 1 over 2, but we're going to substitute 2x cubed minus 1 in for x in the g function, and then plus 1. Now the 1's cancel, and you would have the cube root of 2x cubed over 2. The 2's cancel, and you would have the cube root of x cubed, which is just x. So since f of g of x equals x and g of f of x equals x, you can conclude that those two functions are inverses of one another. So I just want to verify this in Desmos. So here we have our functions. In red is the original function. In G, you have the inverse function in blue. And notice they are reflections of one another over the line y equals x. Put it in dotted line there. So if you noticed that graphically a function and its inverse are reflections of one another over the line y equals x. If you take a peek back at the graph, you can see here that the red and blue functions are reflections over the line y equals x. So the next thing we want to talk about in this video is to verify the existence of an inverse function. Now, it's important to note that not every function has an inverse. And to test this, we would use what's called the horizontal line test. Basically, it's like the vertical line test for testing for functions, except you test it with a horizontal line. If a function passes the horizontal line test, then it's said to be a one-to-one function. And if a function is one-to-one, then it will have an inverse. Or if a function has an inverse, then it has to be 1-to-1. So what we're going to do is look at a couple examples here of which function has an inverse. So if we graph these functions, we can get an idea of whether or not it has an inverse. So first we have the graph of f of x, x cubed minus 1. And if we look at the graph, we know it's cubic, and it looks like it's 1-to-1 because no matter where we pick a point, if we pass a horizontal line through it, no matter where we go on the graph, it would pass the horizontal line test. Now, if we look at the other function, notice if we pass a horizontal line, say at y equals 1, you can see that it crosses more than one time. So all a function has to do is not pass the horizontal line test even once, and it would fail to have an inverse. Now, one of the ways to verify that a function has an inverse is to show that if you have basically two different points, we'll call them x1 and x2. And to show that x1 evaluated in the function is got to equal x2 only if x1 equals x2. So what we do, just plug x1 and x2 into the function. So we'll do the first one. So that would be x1 cubed minus 1. We want to know, does that equal x2 cubed minus 1? Well, just add 1 to each side, and then you would have x1 cubed equals x2 cubed. And then take the cube root of each side, you would have x1 equals x2. What this means is that f of x1 is going to equal f of x2 only if x1 equals x2. So since x1 has to equal x2, it follows that f is 1-to-1. And since it's 1-to-1, you can conclude that that function must have an inverse. Now, for b, we looked at the graph and verified graphically that it doesn't have an inverse. In fact, as long as you find two x values that produce the same y value, so if you plug 1 or -1, or in fact even 0 into the function, all of those equal 1. So that's 1, 2, 3 x values that produce the same y value. So this function is not going to have an inverse because it's not 1-to-1. 1-to-1 basically means for each x value, there's only one y value, and for each y value, there's only one x value. So this can get a little bit tedious, and often it's easier to prove that a function has an inverse than to find the actual inverse function. So for example, if we look at the graph of x cubed plus x minus 1, so we can see by the graph that it appears to be 1-to-1. In other words, an inverse will exist, but it would be very difficult to determine the inverse function algebraically for this cubic function. So let's take a look at example 3 here. We want to find the inverse function for 2x minus 3. Now first, you have to determine whether the function has an inverse or not. So you could look at the graph and just kind of see it from there. Then you want to solve for the inverse function. So if you let this equal to y equals square root 2x minus 3, then the next step is to interchange x and y. So y equals square root 2y minus 3. X equals square root 2y minus 3. And then square both sides. X squared equals 2y minus 3. Then solve by adding 3. So x squared plus 3 equals 2y. And then divide by 2. So y equals x squared plus 3 over 2. And then you can rewrite using inverse notation. So f inverse of x would equal x squared plus 3 over 2. Another important aspect is to determine the domain and range of the original function so that you know the domain and range of the inverse function. So for this function, the domain is 3/2 to infinity, because 3/2 is the smallest number before you start getting negatives. And then the range would be from 0 to infinity. So for the inverse function, we would have to define the domain as from 0 to infinity, and the range 3/2 to infinity. So we'll take a peek at what this looks like in Desmos. So here in blue is the original function. I've graphed the inverse here, and this inequality here is just restricting the domain. If I didn't have that on there, then you would see the entire parabola, but that is not the true inverse function. An important thing to remember is that if a function is not one-to-one on its entire domain, you can actually restrict the domain to an interval which it is. Then the new function would have an inverse function on this restricted domain. So an example for this is to show that sine is not one-to-one, but it would be one-to-one if we restrict the domain to -π/2 to π/2. So here we have the sine function, and you could definitely see it does not pass the horizontal line test. If we restrict the domain, you can see that an inverse function would exist. Now, this brings up the important concept of inverse trigonometric functions. None of the 6 basic trig functions have inverse functions. However, if we graph them, we can see that if we restrict their domains, we can make inverse trigonometric functions. In an example 4 that we just did, we restricted the domain of the sine function so that on the interval -π/2 to π/2, it was one-to-one. So on that interval, that restricted interval, we would have an inverse function. And we notate it with arcsine. This is the inverse function of sine. Sometimes you may see it noted like this with the -1 exponent. Either notation is fine. Just be careful that this is not equal to 1 over sine x. Okay, so just be careful there. I have my original function sine x here. It's one-to-one on the interval -π/2 to π/2. If I graph arcsine, and notice that it is a reflection of the sine function over the line y equals x, which is one of the properties of inverse functions. Now we can go through this kind of process with all 6 trig functions. Here are the definitions of all 6 trig functions and their inverses, and the corresponding domain and range of the inverse functions. Now, you don't have to memorize this list, but make sure if you need it, you can refer back to it. Also, here are the graphs of the 6 inverse trig functions. Again, you don't have to have these memorized, but it's good to have an idea of what they look like and be able to refer back to this as needed. Another thing that's important to remember is that we are always, always, always going to use radian measure when working with inverse trig functions. In fact, throughout the course, it's always going to be assumed that we're using radian measure instead of degrees. The only time you might switch to degrees is if a problem specifically says to use degrees. But be careful, if you're also taking a physics course, some other math related courses may use degrees. So just be careful there. If we go back to Desmos and you click on the little wrench here, you can make sure you're in radian mode by switching back and forth down here. If I click degrees, notice how the graphs change drastically because they would be different if x is in terms of degrees. So make sure you're in radians. Now we could talk a little bit about evaluating expressions involving inverse trig functions. So if we have arcsine of -1/2, since y equals arcsine of -1/2, that implies that sine of y equals -1/2. Since sine y equals -1/2 2 times on the unit circle, we would not have 2 answers here though, because we only want the answer that is on the restricted interval -π/2 to π/2. So y would be equal to -π/6 in this case. Similarly, for arc cosine of 0, by definition, this implies that sine cosine of y is equal to 0. Now, remember, the inverse cosine function, if we look back up here, has a different restricted domain. It's from -1 to 1, and the range is from 0 to pi. So we're restricting cosine to be from 0 to pi, and on that interval, y is equal to pi over 2. So we would have that answer there. Again, by definition of y equals arctangent of root 3, the tangent of y got to equal square root 3. Now, on the interval, the restricted interval here for arctangent, the range is -pi/2 to pi/2, which was the y values. So we want the corresponding y value, which would be pi/3, because tangent of pi/3 is root 3. Now for this last one, this is not a special trig angle, so we would make sure our Desmos is in radian mode and then calculate it on there. So just literally type in arcsin, ARCSIN, use your parentheses 0.3, and it will automatically give you your answer, 0.3047. Remember, when we're dealing with properties of inverse trig functions, that the trig functions they are based on are only valid on their restricted domain. So for example, if we have the tangent inverse of the tangent of 3 pi over 4, that is not going to be equal to 3 pi over 4. It is true that tangent inverse is going to, quote, undo the tangent, but only for values on the restricted domain. So what we could do in this case is we know that tangent of 3 pi over 4 is equal to -1. So then we could do the tangent inverse of -1, and that's going to be -pi over 4 because the domain is restricted to values between -pi/2 and pi/2. So we have to keep this in mind whenever we are working with inverse trig functions. And that's why I said it's important to be able to refer back to these graphs and these definitions of the functions in their domain and range. So if we want to solve this equation, the first thing we do is take the tangent of each side. So if we take the tangent here and the tangent here, tangent of the arctan is going to cancel, and you get 2x minus 3 equals tangent of pi over 4 is just 1. And then if we solve that equation, add 3, divide by 2, you would have x equals 2. Now, the reason we could just do the tangent and the arctangent canceling one another here is because what it was set equal to was pi over 4, and pi over 4 is part of the restricted domain, so we didn't have to adjust for anything. Now, in some cases, you may need to use a right triangle to solve a problem involving inverse trig functions. So for example, if we have arcsine of x where y is between 0 and pi over 2, we want to find cosine of y. So because y equals arcsine of x, you know that sine of y, if I take the sine of both sides, sine of y has got to be equal to x. This relationship between x and y can be represented by a right triangle. So if I draw my right triangle, the angle here is going to be y. This is the right angle. And remember, sine is opposite over hypotenuse. Since it's just equal to x here, we can understand that it's x over 1. So the opposite is going to be x. The hypotenuse is going to be 1. Then we could use the Pythagorean theorem to solve for the other side. So that's going to end up being 1 minus x squared. So cosine of y, which is what we wanted to find, is equal to the adjacent side over the hypotenuse, which is square root 1 minus x squared over 1, or just square root 1 minus x squared. Now for the next one, y equals arcsecant root 5 over 2, we want to find tangent of y. So the first thing we have to do is take the secant of both sides. So secant y is equal to root 5 over 2, because the secant of arcsecant is going to cancel in this case. Then we are going to set up our right triangle with the angle y right here. Now remember, secant is hypotenuse over adjacent. So we know that the adjacent side is going to be 2 and the hypotenuse is going to be root 5. Now, if you use the Pythagorean theorem and solve for the missing side, turns out that this is going to be equal to 1. Now, if I want to get the tangent of y is equal to opposite over adjacent, so 1 over 2, or 1/2. All right, guys, that's it for this video. Hope that was helpful. Reach out if you have any questions, and take care.